Welcome to the discussion. Week 1, day 4. Week 1, day 4. Let's move into. Right. Here we go. First question here. A proton enters perpendicular to a uniform magnetic field of flux density 0.017 Tesla with velocity 8 10 to the power 5 meters per second as shown in the diagram. There you go. That's a proton entering. The magnetic field is directed into the paper. Magnetic field is directed into the paper. So you can see this means magnetic field is into the paper. Magnetic field is into the paper. Right. Magnetic field is into the paper. Charge of the proton is given 1.6 10 to the power minus 19 coulomb. And mass of the proton is given here 1.7 10 to the power minus 27. 1.7 10 to the power minus 27. Right. So if I keep moving, explain why the path of the proton in the magnetic field is circular. Find the radius of the path, copy the given diagram and draw a rough sketch of the path of the proton on it. Right. Now look at this book. Now when this proton enters the magnetic field, now remember proton is positively charged. Right. You can apply Fleming's left-hand rule. Now, what do you mean by Fleming's left-hand rule? If I draw it here very carefully for you, what do you mean by Fleming's left-hand rule? Look at the board. Fleming's left-hand rule means if you take the left hand, thumb, first finger and second finger, the thumb, first finger and second finger, and if you keep it perpendicular to each other, the thumb, first finger and second finger, if you keep it perpendicular to each other, the thumb will give you direction of force. First finger will give you direction of field. Second finger will give you direction of current. Now remember, current means direction that the positive charges travel. Or opposite to the direction that the electrons travel. So here, force, field, current. Right. Now we're going to apply this. If I go here, if I apply it, field inwards, positive charge going in that direction, current same direction, field, current, force. So here you will get force acting in that direction. And here you can see the velocity of the particle and the force are perpendicular to each other. If I mark it here, velocity of the particle and force are perpendicular to each other. What will happen? Now this will cause the charge to go in a circular path. Now it will try to alter the path. Now I'll draw in dotted lines, alter the path. There you go. Now again the proton is here. The proton is there. We can say the tangential speed is the same V. If I move it slightly down here, tangential speed is same V. Now if you apply the required left-hand rule, again what? Field inwards, positive charge in that direction, force. Field, current, force. Force is acting perpendicular to the velocity. And if I extend this, it's directed towards the single point. Now the force is perpendicular to the velocity, and these forces are directed towards the single point means what? We only have learned this earlier in circular motion. So you can say here point form if you write it, first point you write it. Magnetic force, I'll write like this, magnetic force. Better to write in words. Magnetic force magnetic force is perpendicular to the velocity, right? Second point, the path of the proton will change, right? No? Path of the proton will change. Next one, the magnetic force will always be perpendicular to the velocity and directed towards the center. Directed towards the center. Directed towards the center. Therefore, the proton will travel. Proton will travel in a circular path. Proton will travel in a circular path. Right. Now, if you want to find the radius of the path, find the radius of the path. Here we can write it, we can find it. Radius of the path we can find. Centripetal force equals mass into centripetal acceleration acting towards the center. Acting towards the center. Centripetal force is given by the magnetic force V squared over R. Magnetic force is given by the equation BQV. BQV. MV squared over R. V cancel off. Radius is equal to MV over BQ. Radius is equal to MV over BQ. Do the substitution now carefully. They are given you the mass 1.7 10 to the power minus 27. Charge is given. And magnetic field is also given 0.017 Tesla. Right? No? So if you write this very carefully, apply it very carefully. Substitute here 1.7 10 to the power minus 27. Velocity 8 10 to the power 5. Magnetic field 0.017 Tesla. Charge is 1.6 10 to the power minus 19. Now simplify the relationship. Once you simplify the relationship, you will get the answer. 0.5 meters. 0.5 meters. There you go. So radius is given by the relationship 0.5 meters. Right. Now look at this. Second part. If instead an electron enters with the same velocity in a similar manner, how does the path differ from the path of the proton? Now here, magnetic field is here. Magnetic field is here. Electron is here. Enters with a velocity v. Now apply left hand rule. Field, electron in that direction means current will be in the opposite direction. Field, current, force. Now the force is acting downward. Magnetic force acting downward. Now it will travel in a different circular path. Different circular path. If instead the electron enters with the same velocity with a similar manner, how does its path differ from the path of the proton? So there you go. you can say it will curve downward. The path will curve downward. You know, the path will curve downward. Very direct relationship. Right. If you want, you can find the radius as well. Centripetal force, if you look at it in a different way, yeah. But they have not given you the charge or the mass of the electron, so the radius will be downward. Right. Move on. Deduce the radius of the orbit of a particle entering this magnetic field with the same velocity in a similar manner. Same velocity in a similar manner. It should be alpha particle. Huh? Here, small correction actually. Deduce the radius orbit of an alpha particle. Alpha particle, not this. A. Right. Now, what's an alpha particle? 4-2. Mass number is 4. Mass number is 4. Mass number is 4. Proton number is 2. Proton number is 2. Okay. Mass number is 4. Proton number is 2. What does that mean? That means the mass of an alpha particle is 4 times the mass of a proton. 4 times the mass of a proton. And the charge of an alpha particle is 2 times the charge of a proton. Right. Now they're asking you, this is the magnetic field. This is the magnetic field. What will happen if an alpha particle enters? What will happen when an alpha particle enters? Alpha particle enters, again positive charge, field, current force. Magnetic force, it will bend inwards, right? Now, if you look at this earlier one, if you look at this earlier relationship, radius equal mv over bq. Magnetic field is constant, velocity is constant, radius is proportional to mass to charge ratio. Mass to charge ratio. So I can do the question here. So Roman 2, radius of the proton is mass of the proton over charge of the proton. Radius of alpha particle is proportional to 4 times mass of proton, 2 times charge of proton. Radius of alpha, 2 times mass of proton over charge of proton. Equation 2. Now divide the first equation by the second equation. 1 divided by 2 or 2 divided by 1. Radius of alpha over radius of proton. 2 times mass of proton over charge of proton. Mass of proton over charge of proton 2. Radius of proton 0.5. Cross multiply. Radius of the alpha particle 1 meter. Radius of the alpha particle 1 meter. Easily we can find this. Easily we can find. Right. So since we found the radius of the alpha particle, radius of alpha particle will be 1 meter. 1 meter. Okay, moving on. If a neutron enters a magnetic field, in a similar manner, show its path on the diagram drawn. I'll draw it here. Here you have a magnetic field. Here you have a magnetic field. And if a neutron enters this magnetic field, what will happen? Remember, neutron has no charge. It's a neutral or no charge. neutral particle. No charge means you can't apply Fleming's left hand rule. That means no force. The neutron will travel undeviated. No magnetic force. No magnetic force will act on the charge. No magnetic force will act on the neutron. Therefore, it will travel undeviated. It will travel undeviated. They are asking you to draw this in the earlier picture. I'll do it here so that you'll have some clarity. Right. Moving on. If a suitable uniform electric field is now applied, in addition to the magnetic field, the deflection of particles due to the magnetic field can be nullified. Find the magnetic direction of this electric field for a proton. Now here you go. This is your magnetic field into the paper. If we take a proton, proton is traveling this way. Field current force. The magnetic force will act in the upward direction. Here you go. Magnetic force will act in the upward direction. So how do you nullify this? Nullify this means there should be an electric force acting downward. Now, positive charges, protons are attracted to the negative particle. So, electric field should be downward because electric field travels from plus to minus. So, down you have negative. So, proton is attracted to the negative. Therefore, here, if I mark it with a different color, maybe, it is much more clearer. Here you go. There you go. That will be your electric force. That will be your electric force acting downward. Magnetic force upwards, electric force downwards. There you go. They're asking you to find the value for this, so you can find it easily. Magnetic force balances the electric force. Magnetic force equals BQV. Electric force is equal to EQ. QQ cancel off. Electric field is equal to B times V. So our magnetic field is how much? 0.017 Tesla. 0.017 Tesla. Right, no? 0.017 Tesla, that was given earlier. 0.017 Tesla. Velocity is given. Velocity is given. Velocity is given. Velocity is 8 × 10⁵ meters per second. From this, you can find the required electric field in newtons per coulomb or volts per meter. Newtons per coulomb or volts per meter. What will be the value? The value will be 1.36 10⁴. 1.36 10⁴. There you go. 1.36 10⁴. Then they are asking you, will there be any changes to the velocity? No resultant force. No resultant force. Therefore, no change in the velocity. No change in the velocity. No resultant force. Therefore, no change in the velocity. Yeah. No change in the velocity. Right. Right. Next question. Read the question carefully. Write down Poisson's equation for streamline flow. Write down Poisson's equation for streamline flow. Look at this carefully. So question number 2, Poisson's equation, volume flow rate. I'll name the symbols Q dot. Volume flow rate. Volume flow rate. Delta P, difference in pressure. Difference in pressure. L, length of tube. Length of tube. Eta, coefficient of viscosity. Coefficient of viscosity. Then R, Radius of capillary tube. Radius of capillary tube. Okay. Radius of capillary tube. They're asking you to relate or show the relationship Q dot equals pi over 8 eta L R to the power 4 delta P. R to the power 4 delta P. So this is your Poisson's equation for the volume flow rate through a capillary tube. Volume flow rate through a capillary tube. Right. That is done. Poisson's equation done. Identify all symbols done. Draw a label diagram of an experimental setup used in a school laboratory to find the coefficient of viscosity of water using the above equation. Let's do that. I'll show it here. Let's go to the next page. So what we do is we have a constant pressure head. Constant pressure head. Here you go the overflow. Right. Here we go the overflow. Here we can have a small inlet. Water in. This is the overflow. That means we always try to maintain this height. Always try to maintain this height. Right. Then we have a capillary tube connected here. Capillary tube connected here. Here we can draw a stand. Then there is going to be a small piece of string connected here. We are going to have a beaker, or we can say measuring flask. Lots of water falling in. There you go. Here you must have a stop clock or a stopwatch. Length of the tube is here. Radius of the tube, I think we have spoken about this. Simple R. This is your stand. Maintain this at a particular height always. You call this constant pressure head device. Constant pressure head device. Constant pressure head device. Okay, now constant pressure head device. So this is your diagram. This is your measuring cylinder. Measuring cylinder or flask. Water is flowing through. Here it's going to be water. Water. This is your piece of string. Why do you put a piece of string? So that it will fall drop by drop. Drop by drop, streamline flow is maintained. Flow velocity is going to be very, very low. Right. Okay. That is also done. Briefly state the procedure that should be adapted to enhance the accuracy of the final result. Briefly state the procedure that should be adapted. This one. To enhance the accuracy of the final result. Now that means you're trying to find the coefficient of viscosity. Yeah. So what should you do? What should you do? Look at the word carefully. These are things that you should do. Number one, you must maintain or must clean the tube. Clean the capillary tube. With nitric acid or HCl, sodium hydroxide, and in water and clean water. Next one, what will you do? Make sure you maintain a constant pressure head. So the tube must be horizontal. Tube must be horizontal. Things can go wrong, huh? So it will make it horizontal. Next is measure radius. You can't measure the radius. Measure mean diameter of tube. Mean diameter of tube accurately. Accurately. Measure mean diameter of tube accurately. Okay. Then what else should you do? Allow water to collect for a long period of time to increase the accuracy. Yeah? Allow water to collect for a long period of time. Long period of time. Put a string so that water drops fall. Water drops are falling means it indicates what streamline flow. Very important, huh? Streamline flow. Also, so many things. Maintain constant h, constant height. Always maintain constant height. And flow rate should be very slow. Flow rate must be very slow. So if you can do all of these things, you can make sure you can accurately measure the coefficient of viscosity. You know? So around the same setup, I wrote everything to measure eta accurately. To measure eta accurately, what you should do. Right. That is also done. So all these are part of the main question, but you must underline and make sure you do it. Huh? Figure shows a rough sketch of a syringe that can be used to inject liquid to the blood vein. The liquid inside slowly pushed out through the needle AB. This is your needle AB. Small means like capillary tube, so we can apply Poisson's equation there. Here it's very large, so there, of course, pressure will remain constant. The liquid inside the tube is pushed throughout the needle by applying constant force on D. Length of the needle is 2 centimeter. So length of the needle is 2 centimeter means if I show it here, this is 2 centimeter. Okay, that is 2 centimeter. And its bow has a radius 0.02 centimeter. Assume that the velocity of the liquid inside the tube is negligibly small under the situation. Draw the variation of pressure along the tube along the axis from C to B. CAB. So what can you say here? C to A to B. C to A, the pressure is constant. A to B, right, just get it accurate. A to B, constant pressure gradient. Constant pressure gradient. Right, no? Right, next one. When the NB of the needle is exposed to the atmosphere, the time taken to push 1 cubic centimeters of liquid through needle is 10 seconds. So volume flow rate can be found. Coefficient of viscosity is given. Remember, coefficient of viscosity here is 10 to the power minus 3. Yeah? 10 to the power minus 3. If I look at the original question, it should be 10 to the power minus 3. So this is wrong. I'll cut it. 1 10 to the power minus 3. Yeah? Calculate the pressure difference across AB. So you can say Q dot is equal to pi over 8 eta L R to the power 4 delta P. They are asking the pressure difference across AB. Calculate the pressure difference across AB, across the needle. So volume flow rate is volume. Cubic centimeters convert to cubic meters divided by time. Pi here. Radius is given in centimeters, 0.02 centimeters. Convert to meters to the power 4. Delta P is your pressure difference. 8 eta is 10 to the power minus 3. Length is 2 centimeters, convert to meters. There you go. From this, we can find the pressure difference, delta P, cross multiply. Delta P, take it, 10 to the power minus 7 times 16, 10 to the power minus 5. I'm just multiplying it, 2 times 8, 16. Here minus 3, minus 2, minus 5. On top you have pi divided by, or pi times. Here 2, 10 to the power minus 4. 2 to the power 4, minus 4, minus 16. Simplify this carefully. 16 here, 16 cancel off. Here delta P is equal to, on top you have 10 to the power minus 12, here 10 to the power positive 16. 7 divided by 22. Delta P. Simplify the relationship there. 7 divided by 22. Pressure difference can be easily found. 3.2 10 to the power 3. 3.2 10 to the power 3 Pascal. That's the pressure difference between the across the needle. Across the needle. Right. Moving on. Assuming that the average excess blood pressure over atmospheric pressure is 100 millimeter mercury. That means inside your blood, the blood pressure is 100 millimeter mercury. Calculate the additional force to be applied on D in order to inject 1 cubic centimeters of blood into the blood vein in 10 seconds. Density of mercury, actually this is 13.6, 10 to the power 3, okay, 10 to the power 3. Cross-sectional area of the piston is given. Now look, when it comes to the atmosphere, I've seen the nurses, no, they press like that, atmospheric, okay, then you are applying a certain force. Now to push the liquid in, you must have an additional force applied. Additional force applied. Why? Pressure inside the blood veins. Now let's say this is a person's hand. We are inserting this needle. We are inserting this needle. Sorry. We are inserting this needle. Inserting this needle inside like this. And we are now pressing. Pressing. Inside the person's blood, it's going to be blood pressure. Outside the edge, different story. Now you have to apply some pressure to push this liquid in. This liquid to go inside because your blood pressure is there. So blood pressure is the one resisting the motion inside. Yeah. Blood pressure only is resisting the motion inside. Okay. So here if you apply it, now if you look at it, I'll draw it again. Here, piston is here. You're going to push here. Now the pressure here is not the same pressure, not atmospheric pressure. Now here pressure inside, blood pressure is given. They are giving you, assume that the average excess blood pressure over atmospheric pressure is 100 millimeter mercury. Calculate the additional force to be applied on D in order to inject 1 cubic centimeter of liquid into the blood vein. So this is, I think, C, A, B, no? Same volume flow rate. Think carefully and answer. Q dot is equal to pi over A theta L. L won't change. Radius won't change. Delta P. If you look at this earlier case and this case, all these variables are same. All these variables are same, including the volume flow rate. So volume flow rate is also same. So earlier situation, pressure difference. Q dot proportional to earlier pressure A minus pressure B. Earlier pressure A minus pressure B. If you look at the picture here, AB, right? Pressure A minus pressure B that we found. 3.2 10 to the power 3 Pascal. New situation, pressure A minus new pressure here, pressure P dash. Same volume flow rate. Can you say about 1 and 2? 1 and 2 are equal. So if you divide 1 and 2, from there you will get these two will cancel off. PA minus PB dash equals PA minus PB, pressure difference. Right? No? There will be a pressure difference there. So earlier pressure difference found. Earlier pressure difference you found. So these PA double dash, I think. PA double dash. PA double dash. Right. So new pressure at this end. New pressure at that end. New pressure here, PB. Pressure at B dash. Equals earlier pressure difference. Equals earlier pressure difference. Why the volume flow rate is same? All these variables are same. Technically pressure difference should be same. If volume flow rate is same, this part is same, that part is same, pressure difference is same. Now from here, if I divide 1 by 2, you can get this basic relationship. Basic relationship. Look at the board now. So we can go to the calculating board and solve this out. PA double dash minus PB dash, PA minus PB. PB dash is the pressure 100 millimeter mercury, right? Earlier pressure 3.2 10 to the power 3, right? Simplify this. PA double dash minus PB dash, PA minus PB. Earlier pressure difference is equal to 3.2 10 to the power 3. 3.2 10 to the power 3. PA double dash pressure difference there. PB dash is 100 millimeter mercury over atmospheric pressure. 100 millimeter mercury over atmospheric pressure. H rho G. PA double dash equals 3.2 10 to the power 3 plus H rho G. 3.2 10 to the power 3. Height is 100 millimeter, convert to meter. 13,600 times G. 20 here, 0 here, 0 here, cancel off. 3.2 10 to the power 3 plus 13.6 10 to the power 3. So if I simplify this, I'll get 13.8 10 to the power 3 or 1.38 10 to the power 4 Pascal. 1.38 10 to the power 4 Pascal. Okay, no? 1.38 10 to the power 4 Pascal. Right. Now, what is the excess force applied on D? Piston cylinder arrangement. Outside you are having atmospheric pressure. Inside here pressure now PA double dash. Horizontal means pressure is same, here also PA double dash. So the atmospheric pressure you are applying a force, no? This PA double dash is more than the atmospheric pressure or less? 10 to the power 4, no? Right. So PA double dash 1.38 10 to the power 4. 1.38 10 to the power 4. So 100 millimeter, 0.1 meter, 10, 13,600, 3.2 10 to the power 3. That's your pressure at A, PA double dash found. PA double dash here. Now, if you are pushing this, you have to create a larger pressure, no? If you are pushing this, you must create a larger pressure. Now, how will you create the larger pressure? Right. So, what we can see here now is PA double dash is 1.38 10 to the power 4. This is inside your, this is your new inside pressure. New inside pressure. Inside pressure there. So, if you look at it carefully, the pressure at B has changed. The new pressure there at A is this value. Okay. So if I draw it for y'all, this is initially A and B. This is finally, here pressure is PA, pressure PB. Now PA double dash, PB dash. You can see the pressure difference here. PA minus PB equals PA double dash, PB dash. If you simplify it carefully, PB dash minus PB equals PA double dash minus PA. That means the pressure change here and the pressure change at this edge both should be what? Same. So what is happening is there is going to be a pressure change here. There is going to be a pressure change there. Here open to the atmosphere, here atmospheric pressure. Here they are telling you, if you look at it carefully, here they are telling you, assume the average excess blood pressure over the atmospheric pressure. That means PATM plus H rho G. PATM plus H rho G. So here if you look at it, here it's going to be PATM plus H rho G. So the pressure increase here and the pressure increase there both are same. Here PA double dash minus PA and PB dash minus PB both are same. So what is happening is you have to apply a force to overcome this excess pressure. Overcome this excess pressure. Okay, no? So PA double dash we have 1.38 10 to the power 4. PA we don't know, but don't worry. What is PB dash? PATM plus H rho G. What is PB? PATM. So the excess pressure here and the excess pressure there both are what? Same. So something you should remember in this question. If I go back again. Now when the fluid is traveling through this, here we found out from the earlier relationship the pressure differences are equal. Pressure differences are equal for PB dash, we did the substitution here. The best thing is This PA double dash value is no need. Actually, no need to find this. No need to find this at all. Because you are dealing with the pressure difference. No? So the pressure difference here, the increase in pressure there, and the pressure difference here both are same. So if I apply very carefully, excess pressure at B equals excess pressure at A. What is the excess pressure at B? The difference here. PATM H rho G minus PATM. Excess pressure at A is PA double dash minus PA. Simplify this, H rho G you will get. H rho G is equal to 100 millimeter convert to meter. 13,600 into 10. That's your excess pressure. Excess pressure at A. Simplify the relationship. Excess pressure at A. For this excess pressure only, a force is generated. 1.36 10 to the power 4 Pascal. 1.36 10 to the power 4 Pascal. So when I'm pushing this, when I'm applying a force, there's going to be an excess pressure here, the pressure difference here. For the pressure difference only I have to apply. Okay, no? So the force applied is equal to 1.36 10 to the power 4 times 0.75 centimeter square 10 to the power minus 4. 1.36 3 divided by 4. 0.34 times 3. 12, 10, 2 decimal places, 1.02 Newton. You're applying 1.02 Newton. So clear now? So here, when you're pushing a liquid in, remember at the end of the needle, very important concept. At the end of the needle, there will be a pressure difference. You're applying a force equal to the pressure difference here. There. You're applying a force equal to the pressure difference here. The pressure difference here, to overcome that only, you're applying the external. You know? Right. Okay. Right. Then comes your current question. Right. Answer either part A or part B. Normally, these are electricity and electronics are selection question. But either one of the two, you have to select and do. I'll do both of them because it's important. Right. Here we go. A 60 watt light bulb is connected to a 12 volts voltage source of a copper wire. The bulb lights with full brightness. Calculate the current through it. So power is equal to VI. Full brightness means energy consumption is maximum. Power is maximum. 12 times current. Current is equal to 5 amperes. Current is equal to 5 amperes. Right. Moving on. Consider that each copper atom contributes 1 electron. Each copper atom contributes 1 electron. Calculate the number of conduction electrons in 1 cubic meter of copper. 1 cubic meter of copper. You know? So density is mass over volume. Density is mass over volume. So per cubic meter, we have 9,000 kilograms of what? Copper. 9,000 kilograms of copper. Look at this very carefully. Avogadro number is given means how much? 63 grams of copper has Avogadro number of atoms. One atom gives 1 electron. So 1 gram of copper, 6 divided by 63, 10 to the power 23 electrons. Now how much? 9,000 kilograms. 9,000 kilogram is 9 10 to the power 6 grams. 9 10 to the power 6 grams, or we say 9,000 kilograms of copper. 6 divided by 63 multiplied by 10 to the power 23 multiplied by 9 10 to the power 6. From this we can find the number of electrons. From this we can find the number of electrons. How much? If you simplify the relationship there, number of electrons. So 63 grams have Avogadro number of electrons. 1 gram has so much. Altogether how much? Altogether how much? If you simplify the relationship here, how much? 6 10 to the power 6. There you go. 54 over 63. 8.57. 8.57. 10 to the power 29. 10 to the power 28. Electrons per cubic meter. Electrons per cubic meter. 8.57 10 to the power 28 electrons. Where? In 9,000 kilogram. 9,000 kilogram means in 1 cubic meter. Therefore, you can easily say, simple n is 8.57 10 to the power 28 per cubic meter. Right. Moving on. The radius of the copper wire is given. Calculate the drift velocity. We know the famous equation. I is equal to ANEVD, drift velocity. Drift velocity is equal to I divided by ANE. I divided by ANE. So the current we found earlier, 5 amperes. Cross-sectional area pi. Radius is 0.7 millimeter, convert to meter squared. N is 8.57 10 to the power 28. Charge of electron is 1.6 10 to the power minus 19 coulomb. Simplify this, you can get your drift velocity in meters per second. It will be a very small value. Very small value. The value is how much? 2.4 10 to the power minus 4. 2.4 10 to the power minus 4 meters per second. Right, moving on. Assume that the conduction electrons act like molecules in a perfect gas. Determine the root mean squared velocity of electrons at 27. Now, root mean squared velocity, VRMS. VRMS is 3RT as a molecule, then 3KT. 3KT. 3KT divided by mass of one molecule. Substitute now. Boltzmann constant is given 1.4 10 to the power minus 23. Temperature 300 Kelvin divided by mass of one electron is like mass of one molecule, 9.1 10 to the power minus 31 whole thing square root. Whole thing square root. If you simplify the relationship here, 1.2 10 to the power 5 meters per second. Root mean squared velocity is 1.2 10 to the power 5 meters per second. Explain why there is a vast difference between drift velocity and VRMS. So, why is there a big difference here? Number one, electrons are not ideal gases. Simple. First important property. Electrons are not ideal gases traveling randomly. There will be collision. Okay. So VRMS measures how electrons will act like gases, travel randomly, collide with other particles, and move. But in a conductor, electrons are traveling across what? An electron field or electric field uniformly. Yeah. So therefore, that is the main difference. Right there. In root mean squared velocity, we consider electrons as an ideal gas. 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 Colliding randomly with other particles and moving. Colliding with other particles and moving. In random direction. In random direction. But in drift velocity. But in drift velocity. But in drift velocity. We measure how electrons travel. We measure how electrons travel inside a conductor. Inside a conductor. Due to a electric field. Due to a electric field. Due to a electric field. Okay, next one. If the length of the wire is 1 meter, what is the time taken by an electron to travel from one end of the wire to the other end? Time taken is equal to distance divided by speed. Distance divided by speed. One end to the other end means 1 meter. Speed is equal to, you must consider the drift velocity speed, 2.4 10 to the power minus 4. 2.4 10 to the power minus 4. 2.4 10 to the power minus 4 meters per second. If I simplify this, you will get the time to be a very large time. 4.2 10 to the power 3 seconds. 4.2 10 to the power 3 seconds. Technically, it's a huge amount of time. Yeah, huge amount of time. In reality, how the bulb will light as soon as the switch turns on. So how does the bulb light? It's not one electron traveling. Out of many millions of electrons, the first electron will what? Jump across the barrier. That is what you find. Right there. So in a conductor, it's not about one electron going from one end to the other. There are many millions of electrons in line like this. They are traveling very slowly. They are traveling very slowly. And when the switch is turned on, the first electron will jump. This first electron moves and completes the circuit. Right there. In a conductor, it is not about one electron moving. In a conductor, it is not about one electron moving. One electron moving. And when the switch is turned on, the first electron will complete the circuit. The first electron will complete the circuit. This is the reason there is instantaneous current. This is the reason there is instantaneous current. Okay, no? Right. Now comes the electronics question. Draw and symbol of an operation amplifier, clear, identify all the non-inverting input. So here you go. So non-inverting input V plus. Inverting input V2. Output is V3. Actually, output is V3. Here you must have negative supply voltage. Here you can have positive supply voltage. Clearly identify the symbols. I have drawn it correctly. Correctly drawn. Huh? Write an expression relating V1, V2. So output voltage V3 is A times V plus minus V minus. That is your output relationship with open loop gain. Output relationship with open loop gain. Okay, no? Right. Moving on. A 741 op amp, these are op amp in your syllabus, has an open loop gain 10 to the power 5. It's powered with a voltage supply plus or minus 15. Nothing can exceed. The output can never exceed the supply voltage. Huh? So if I do here, output is equal to A times V plus minus V minus 10 to the power 5. V plus is minus 3 millivolts minus 5 millivolts. Simplify this 10 to the power 5. 5 minus 3 is 2. 2 10 to the power minus 3. You will get 200 volts. 200 volts, V3. This is not possible. V3 can never exceed supply. Never exceed supply. Supply voltage. So if it can never exceed supply voltage, what will happen? V3 will saturate. V3 will saturate. Now here V plus is smaller than V2. Or if you take magnitude wise, V3, V1 is 3 millivolts. Here V2 is minus 5 millivolts. So who is bigger? Now it's a negative value there. Negative value there. Who is bigger? Of course, then V1 is bigger. V plus is larger than V minus. Positive supply voltage means plus 15 volts. Reason? V plus is larger than V minus. Minus 3 millivolt is larger than minus 5 millivolts. So output will saturate at the positive supply voltage. Output will saturate at the positive supply voltage. Right? Okay. Something that you should know here. The thing that you should know is, if V plus is larger than V minus, output will saturate at the positive supply voltage. If I write here, output will saturate at the positive supply voltage. Output will saturate at the positive supply voltage. Okay. And if V minus is larger than V plus, output will saturate at the negative supply voltage, minus V. So what has happened here is this one here. Right. Okay. Moving on. You are provided with two resistors, R1, R2. Draw a circuit for a non-inverting amplifier. Non-inverting amplifier. Non-inverting amplifier. If I draw it, non-inverting amplifier. So here we can show R1, R2, P plus, non-inverting amplifier is connected to your output supply, P3. Right. In an experiment, the voltages produced by a thermocouple are in the range 0 to 10 millivolts are to be measured with a voltmeter having full scale deflection 1 volt. So at least magnify and give this now. Draw a circuit diagram to show how the non-inverting amplifier given in Roman 2a is inserted between the thermocouple and the voltmeter in order to obtain a full scale deflection from the voltmeter for 10 millivolt thermocouple output. So now you have to magnify this. If you don't magnify it, you're going to have a problem. How are you going to magnify the circuit? Let's think. Thermocouple is always between two different temperatures. Two different temperatures, right? No? These two are connected with each other. There you go, you're measuring. There you go, you're measuring. This is what you normally do in a thermocouple, no? Normally, this is what you do in a thermocouple. Right. So here 10 millivolt. Now you have to amplify the signal, make it bigger. How will you amplify the signal? Look at this carefully. Now you have an operation amplifier here. Operation amplifier here. One signal or the voltage signal from here should go into V plus. Voltage signal from here should go into V plus. Voltage signal must go into V plus. Here grounded. Here you have the output. R1 here, R2. Okay. Closed loop gain. Nah? If you want, you can ground this as well. Problem? No? You can ground that as well. They are asking the voltmeter measurement. Now think carefully and answer. Now here there is a voltage V plus, here there is a voltage for step voltage V minus. From there you have output. That output only is connected to a voltmeter. Output only is connected to a voltmeter. So the positive terminal is connected to one end, negative terminal should be connected to the other end. You have grounded this. If you want to ground it or directly connect it here. You can directly connect it here as well. So one terminal will go to the negative part. Positive part here is amplified. If you want ground it, grounding also no issue. Normally I prefer if you ground it. To ground this whole setup, it's easy. So just showing it to you all. One terminal goes to the negative part of the voltmeter. The positive part of the voltmeter is here. One is, sorry. If I go back, right. So this is a cold end. That's a hot end. You can connect this end and the other end to a voltmeter. This is one setup. Huh? This is one setup. And using these feedback resistors and input resistors, we can amplify the required circuit and give. So this is one. So this is your diagram. Right. Of the two resistors R1 and R2, if the smaller resistor has value 1 kilovolt, 1 kilo ohm, what should be the value of the other resistor in order to achieve full scale deflection in Roman 2? Full scale deflection means what? You have to achieve full scale deflection here. Full scale deflection is 1 volt. Full scale deflection is 1 volt. So output should be 1 volt if I'm grounding it. So this part I will do just to get it easier. We'll ground the circuit. If you want, bring it here, grounded. Easier. Grounded. This is also grounded. Huh? Either way, it's easy. Then we can just focus on the output here. What is the output here? So full scale deflection, how much? Full scale deflection, 1 volt. 10 millivolt output. So here 10 millivolt. V plus is equal to 10 millivolt. 10 millivolt. Right. Think carefully and work. Think carefully and work. Right. So we have the circuit here. Looking at the circuit, let's work this out. So here, if you look at this closed loop circuit, golden rule none, V plus equal V minus. Golden rule 1. Golden rule 1. V plus is 10 millivolt. V minus is also at 10 millivolt. V minus 10 millivolt. I want a full scale deflection here. So full scale deflection is 1 volt. The output here is going to be 1 volt. Output is going to be out 1 volt. So closed loop gain, output over input, output over input. If you think about the basic, what do you call circuit, it's much more easier. Think about the basic circuit, much more easier, right? So we have current passing through here. We have current passing through here. So current will travel. No current input, golden rule number 2. So current is passing through. Current is passing through. So V output here minus V minus here, V minus there. So if I write the relationship, V output minus V minus, current into R1 in this part. V minus minus 0, current into R2. Current into R2. V minus already we know. Divide one by the other. Divide one by the other. Here, V output minus V minus. V minus minus 0. I cancel off R1 divided by R2. I'll name this equation 1. I'll name this equation 2. Here you have 1 divided by 2. 1 divided by 2. Now what? Your output voltage is 1 volt. V minus is 10 millivolts. Millivolts convert to volts. Millivolts convert to volts. Here also 10 millivolts. What are your values? Smaller resistor. It's a gain. R1 should be larger. Smaller resistor is 1 kilo ohm. What is going to be R1? Simplify the relationship very, very carefully. So here 10 to the power minus 2, 0.01. 0.01 is 0.99. 10 to the power minus 2, first multiply 10 to the power 3, R1. Simplify this. R1 is equal to 99 10 to the power 3 ohm. 99. Which means 99 kilo ohm. 99 kilo ohm. You call that feedback resistor. That's about 99 kilo ohm. 99 kilo ohm. Very easily you can find. So I've shown you the complete method, how to reach there. Golden rule number 1. Then golden rule number 2 is input resistance is infinite. Therefore, no current input. No current input. Right. No current input. If you are provided with another resistor R3 and a two-way key, how would you modify the given circuit in B so it can be used to measure voltage in two ranges, 0 to 10 millivolt and 0 to 100 millivolt separately, with the same voltmeter giving full-scale deflection in either range? The two-way key is used to select the required range. Find a suitable value for R3. Find a suitable value for R3. Look at the board carefully. Now what is changing? Your input range is changing. V plus is changing. When V plus changes, your V minus will also what? Change. Your V minus will also change. So V plus changes, your V minus will also change. R1, if you look at it carefully here, the smaller resistor, the R2 resistor is fixed. So what will change depending on the output? Depending on the output or depending on this V minus, your R1 will change. The R1 will change. So what we can do is we can design something like this. Look at it carefully, yeah. So your cold and hot, two different temperatures. Cold and hot, we don't know, no. One will be hot, one will be cold. Right. Here we connect this to V plus. Non-inverting input. V minus. Grounded. Now, earlier we found 99 kilo ohm. Now we have R3. Two-way switch is there. We can decide which one to use. Depending on that, we can connect it to the voltmeter, which is also grounded. So, if you want, I can ground it here, connect it together, and we can ground it. Okay, now. Now they're asking you to find the value for R3. R3, this is your input, 100 millivolts, full scale deflection. Output going to be 1 volt, no change. Output is going to be 1 volt. And where are you going to connect this? You must connect this here. You're going to connect this here with R3. Connect that with R3. So this will be 0 to 10 millivolt range. That's going to be 0 to 100 millivolt range. R1 value, sorry, R2 value here, 1 kilo ohm. R2 value is 1 kilo ohm, no change. R2 1 kilo ohm. Right. Now looking at this, can you solve it? Yes, you can. How would you solve it? V plus equals V minus equal 100 millivolts. 100 millivolts. 100 millivolts is 0.1 volt. 100 millivolt is 0.1 volt, right? So V plus is known, V minus is known. Now current is going to travel. Current will travel from high potential to low potential. No current input. Here current is I1. Solving from basic. So V output here, I'll name it as V minus. V output minus V minus. I1 times resistance R3. Then V minus grounded. I1 times R1. Divide. V output minus V minus. V minus equals R3 divided by R1. What is your output voltage? Full scale deflection 1 millivolt. V minus is equal to 0.1. V minus equals 0.1. R3. What is R1? R1 they have given earlier. Sorry. R2 they have given. R2 is given how much? 1 kilo ohm. R2 is given 1 kilo ohm. This should be R2, right? 1 kilo ohm. So here you'll have how much? 0.9. 9. R3 is 9 kilo ohm. R3 is 9 kilo ohm. 9 kilo ohm. Okay, no? So what am I doing? You're applying what? Basic theory connected to operational amplifier. Basic theory connected to operational amplifier. Right, moving on. X-ray tube is shown in the figure. Name the components indicated by A. A is anode, target metal. Target metal. B is cathode, or we can say filament. Filament. Filament is there. You know? Right. Why does the X-ray tube have to be evacuated? Otherwise, what will happen? Electrons, when they travel, they'll collide with the particles and what? Lose energy. Electrons will collide with other particles. Other particles inside the tube. Inside the tube and lose energy. Inside the tube and lose energy. What is the use of the voltage supply P2? What is the use of the voltage supply P2? P2 will give you what? The required filament current. Here. P2 will give the required filament current. You know? P2 will give the required filament current. So we can write here gives the required filament current. Gives the required filament current. Moving on. What is the polarity of terminal X of voltage supply P1? Terminal X. Anode terminal X is positive, cathode is minus. So X is going to be positively charged. X is going to be positively charged. Positively charged. Positively charged. Okay, no? Moving on. What factor determines the rate of emission of X-ray photon? Rate of emission of X-ray photons, what factor? The filament current, no? Voltage P1. That means, remember, larger number of electrons emitted, larger number of photons also what? Emitted. Okay. So, here, who decides rate of emission of photons? Rate of emission of photons. Rate of emission of photon equals rate of emission of electrons. Why? We say one electron emits one photon. Therefore, who controls this? Who is controlling this? The filament current. Supply voltage P2 will control it. Supply voltage P2 will control it. So, supply P2 will control it. Supply P2 will control it, right? What factor determines the energy of the photon? Energy of the photons is determined by the potential difference across anode and cathode. Potential difference across the anode and the cathode determines determines the energy of X-ray. Therefore, supply P1. Supply P1. To produce electrons with kinetic energy 5.6 10 to the power minus 15, what is the required voltage of supply voltage P1? Right. So gain in kinetic energy of an electron equals work done on the electron. Work done on the electron. Gain in kinetic energy is 5.6 10 to the power minus 15. Work done is equal to potential difference multiplied by charge. So potential difference is equal to 5.6 10 to the power minus 15 divided by 1.6 10 to the power minus 19. 5.6 10 to the power minus 15 divided by 1.6 10 to the power minus 19 gives you 3.5 10 to the power 4 volts. 3.5 10 to the power 4 volts. Moving on. Maximum energy emitted by the X-ray is equal to the kinetic energy of the electrons hitting. Calculate the wavelength of the X-rays having this maximum energy. So X-ray photons emitted equals maximum kinetic energy. Hc over lambda, photon travels at the speed of light, Ke max. What is lambda? Hc divided by Ke max. If I simplify the relationship, what is H? I think they have given you what H is. Keep going down, you will see it. 6.6 10 to the power minus 34. 6.6 10 to the power minus 34. Speed of light 3 10 to the power 8. Ke max is equal to 5.6. 5.6. 5.6 10 to the power minus 15. 10 to the power minus 15. Lambda wavelength you can find in meters. Lambda wavelength 3.5 10 to the power minus 11. 3.5 10 to the power minus 11 meters. Right now. Give two applications of X-rays related to two different fields. X-rays are used what? For security purposes. And scanning. In airports and ports. You have seen this now? Right. Now, of course, you have this in hotels also, but anyway. What's the next one? X-ray. Use for non-destructive testing. Non-destructive testing. What else? X-rays are also used for what? Medical diagnosis. For medical diagnostic. Next, initial form of treatment for cancer. Initial form of treatment for cancer. Right. In production of X-ray, photons are emitted due to interaction of electrons with matter. Give a situation where electrons are produced due to interaction of photons with matter. What do you call it? Photoelectric effect. Photoelectric effect. Photoelectric effect. So photoelectric effect, you all remember? Photons come, hit the surface, electrons are emitted. So one photon, one electron. One photon. So that's what they're asking. Electrons are produced due to interaction of photons with matter. Photon comes, hits a metal, electrons are emitted. Okay, no? Electrons are emitted. Right. So that concludes the complete 2000 A-level paper. So hope you will continue joining with the program. Make sure you keep on working step by step. So this week we have last week completely we have finished the 2011 paper, and this week we'll be continuing with the 2001 paper. So join, disciplinedly work, so you can, when the exam comes, there is no pressure for you because you have done the work correctly. See you again in the next video.